with this facility is they have automated this part so that you don't have to go and edit the bash file. So I've never done that. I always edit the bash file so that I don't have to run it for each terminal I open. Okay, that's one part. The other part is this. So these are commented out lines. So don't copy them. They're commented out. See, this is the accepted, the hash symbol is the comment out symbol. Okay, these two have to do with the IP connectivity. Now, because we have two computers, right? MATLAB has to know the IP address of the Ubuntu computer. So, this is how you do it. Now, what are these numbers? The 11311 is common to everyone. But the IP address could be different on your machine compared to mine. So you have to go find the IP address. Okay, so IFCONFIG. You can tab complete if you want. See? This is my IP address. I have a setup so that the IP address is static. That means if I shut down the computer and tomorrow I open it again, I won't get a new IP address. That's convenient because otherwise you have to edit the bash file, edit the MATLAB code. Now I don't know what your situation is. My IP config is static. So if you have a static IP, if you log out from your computer, take it home, open it and set it up again, no changes are needed. If you have a static IP. If you have a dynamic IP, I used to have a dynamic IP. When I drive home from work and open the computer, the same program will not run. Then you have to go look up the, run ifconfig, look up the IP and patch it again. Very inconvenient. Now I prefer to put this statement in to the bash file. If I don't, every new window I'll have to type this. Now what is going on there? Let's say you're working on 5 projects in a company, right? So any one of those projects is associated with a certain setup, a certain collection of files. So literally imagine somebody opening all the files, some accountant for a particular customer, right? That's what setting up the environment involves. If you're not using the Turtlebot 3, but you're using some other robot, it's better not to have this command in the bash file. You agree? Because if you're working with multiple robots, it's easier to, or you create, a separate bash file. My point is this. This is used to designate that you're going to work with the Turtlebot 3 robot in this session. And I prefer to put it in. Because if I have a new robot, I prefer to comment this out and have another statement for another robot. It's up to you. But the problem is, if you don't put it here and you forget, it'll flag an error because it won't know what the Turtlebot 3 model parameter is set to. We are using the burger version. They have, I believe, 2 or 3 versions. We are using burger, right? It looks like a burger, hamburger.
We use waffle or waffle burger.
Yeah.
Burger, waffle or waffle.
Right. So I use the burger. The waffle is a little bit bigger, like a pancake. Yeah. So when you have entered this, you need to save it. And when you save it, the existing terminals haven't seen the new bash file. So there is a way of running the bash file again within the terminal. What I prefer to do is to shut down the terminal window and open them again. When you open a terminal window, the bash file automatically runs. So any existing terminals have not seen these changes. Is that clear? So after you create these updates, I prefer to shut down all the terminals and open them again. Ignore this part. This is very special to my setup. See whether you can tab complete your way through that. So hit ROSL and then tab. It will complete cross launch. Then space and put Turtlebot. So complete your way. Get the entire command. I'll tell you in a second what the structure is. So this is launching a node. Cross launch is a node. This is the package directory in which the actual launch file is to be found. Let me repeat. ROS launch is a node. Later you're going to just do it blindly in the next few weeks. But ROS launch is a node. This is the package directory. And the particular launch file is here. In fact, I'm going to show you where it is. Let's suspend this command and use the GUI, this one. So you see, my catkin is here and my turtlebot directory is here. I prefer to put each robot in its own workspace. So every package has this structure. It has build, devel, which you don't care about. It's the internal workings. The source is where all the source files are. Turtlebot free simulations. Because I've done it so many times, I know. I'm not asking you to memorize it. Here is the launch directory and empty word launch. So that last one, that is this particular launch file. So ROS requires that particular structure. ROS launch, package directory, the name of the launch file. I just wanted to convince you that these are not ghost files. They are there right under the directory. When we created the whole setup, we gave you the image, all of this was already there. Now hopefully this will launch. So far no red. See how fast my computer is? Now the colors look horrible because the overhead projector is old. You should see the Turtlebot 3 sitting at the origin. Is everybody able to launch this? No? You get an error? Show the launch command. Yeah. So ROS launch automatically launches the ROS core for you. Yeah. ROS core is like a quick test to see whether all the pieces are there. You don't have to, most of the time you don't have to launch ROS core. ROS launch will launch the ROS core. Sorry about that. Yeah, I should have told you that. So learn to tab it, because if you forget the command, you can also recycle like I did. But it's better to, it's all there in the Robotics manual. It's not something to memorize, but so we're not going forward until everybody is able to see the empty word. So if an old ROS code is running, Control C out of it. And then ROS launch, Turtlebot 3 gazebo. Also, you've gone to a ROS Novatic terminal, right? Oh, I think the burger command, right? We forgot.
Burger command we have to.
Yeah, I'm sorry. I think I skipped that last part. Let's go back here. All right, this one, you also have to insert this.
Okay, so when you push it in, so open up your bash files and push only this last line.
Yeah, type it out very carefully without.
Only this last line, push it into your bash file.
Because blank line is not needed. I just like to create readability, so I put blank lines.
So just this line. So open up bash RC and push just that.
Enter that last line. So that tells the software that you're working with the burger. Yeah, don't insert it somewhere in the middle of the bash RC. So the last line is to tell the system that you're working with the burger robot. There are 3 robots. We are working with the burger. So if you don't say anything, it can't proceed. There's no default. So that's why it doesn't work for some people, because it needs to know which robot you're working with. So you should get you got the empty word.
How you got this gazebo through command?
How did I get this screen?
Yes.
Cross launch. So tab complete your way, because then you get confidence ROSL tab, and then it'll wait, put turtle TURT and complete this command. Now this command is in the Robotics manual. If you ever forget, you can go and look it up there. So by the way, try this. Stop here and say tab. Nothing will happen. Tab. It'll give you all the launch files that are valid. And then you'll find the empty word launch, right? Right? So it'll list every launch file that it can launch. So you don't have to memorize this. I want to launch a couple of their other launch files. But before I do that, so this is an empty word, right? But you can pull obstacles down. Now we are operating with a two-dimensional simulator. So this dimension does not mean anything, right? So some of these obstacles can be resized. I'm going to get to this again tomorrow, but it is possible to resize this. Because what's the point of having such a huge block when the robot is not capable of climbing from this plane anyway? And of course there are other things, we'll get to that tomorrow. But what I want to do now is, I'm going to control C my way out of this. So I'm going to shut down gazebo. This is the live gazebo window, if you remember. You'll have to wait a few seconds because it always does some cleanup. Okay, now. So these are all the launch files available. I want to launch the house. See the house there? House launch. So you don't have to type it in by looking at it. You can just type a few words. H. Right? Okay. See, I typed H, and then tab. It completes it. So learn to use the tab control, tab completion feature rather. Now we can change the perspective. You don't have to look at it from the top because this is not very interesting from some certain points of view. Tomorrow I'll show you how to do some basic manipulation of the environment. You can look at it from ground level or any angle you want. The terminal is here. All the terminals will show up here. So when you click on it, you get this terminal, and if there are multiple terminals, it will put multiple arrows here. So you can see it's quite a nice challenge, if you want to run your robot. Let's say that you want this robot to get out of this house by wall following, right? So you can put the robot somewhere in the middle. Where is the robot? Here, the robot is this one. It looks tiny because we are way up. Tomorrow we can zoom down and look at the robot. So this is the robot, and it's got a desk here, all kinds of things. And you can say, I want the robot to come out of this house on its own. There is one more, we can look at that also. So maybe kill this. These are the three that the Robotics manual suggests. There are others, obviously, other launch files. The Turtlebot 3 word. This one. So let me see if I can get that. T-U-R-T. Word. Did everybody get this? So these are the three words that the Robotics manual has. How to launch this? So the package directory name is the same, the middle part. And then you space and then double tab. And when you double tab, you'll see all the options. One of them will have house in it, the other one will have Turtlebot 3 world, and the other one is the empty world.
So how you select the options?
So you can fill out a few more letters, and then it narrows down the options. If you fill out a few more letters, then it'll only be left with that option. Yeah. So these are pre-created words. You can create your own. If you have a particular challenge and you're actually going to use a real robot outdoors with that challenge, you can first create a simulation of it. The point is this, that in the real world, how many simulations can you create? You don't have enough time, right? But you can create 50 simulations and run it overnight. You can figure out what are the bugs in your software. And then you can have a few select ones that you actually try. You realize trying it on an actual robot is going to take much more than real time. Real time is, the clock time. The actual world is advancing, that's real time. But if you go outside and start to set up things, it takes a heck of a long time. You might take 30 minutes to set up, and then you might get one run. When the battery runs down, you go recharge the battery. So if you have got the 3 worlds, what we're going to do now is, we're going to go back and kill this world and go back to the empty world. Because the last part, I want you to try the MATLAB program I'm going to put on the team's website. So I go back to this world and kill it. Control C. Okay, now, so anytime you want to clear the screen, it's clear. I think in Linux it's clear. Yes. In MATLAB it's something else, CLS or CLC or something. I forget all this. I have to Google it. But clear. Okay. It doesn't clear the previous commands, obviously. See, all of them are showing up. I want the empty world launched. So up arrow takes you back through the history of commands, similar to MATLAB. So I'm going to post this MATLAB program on Teams. It's going to need for you to modify something, at least the IP address, I think. So it's uploaded. Wait a couple of seconds and download drive in circle.m into your MATLAB folder. So drive in circle.m. So your first assessment is going to be an extension of this. So this is a very important program. I'm going to first show you how it operates and make sure that you can operate it. And then the next class, I'll go through every line of code to explain to you what is going on. So it may not work immediately, and one reason it may not work is because over here in this program, in the MATLAB program, I have my own IP address, which never changes, right? I told you I have a static IP. So you see here, 192.168.178.135. You have to, whatever you put into the bash file, that same IP has to be put here within double quotes. We're going to run this program again. Once you're ready, patch your IP in here, right here. Oh, right here, right where? Because you can't see it. Here it is. I had it on my primary screen. So, right here. And then I'm going to run it again, don't worry. Now, there's nothing to be afraid of. I believe in putting a lot of comments in my program. So, a lot of it is comments. I'm almost writing a novel with my comments. So we'll go through each line of code tomorrow. So don't worry about that. But load the program into your MATLAB workspace. Change the IP to whatever is relevant to you. And then let me know that you're ready. At that point, I'll run it again. Open the M file from Teams and modify the IP address. Can I talk you through the program so that even if you can't do it, you'll be able to do it after the class. Because what you're being stopped by is something, it's just a technicality. You can overcome it because somehow you will find the program and be able to download it, I'm sure. After that, you have to fix the IP address. You have to fix the string. Okay, and then I want you to see what's going on in Gazebo. So I'm going to pull this out. And when you make a Gazebo run, right, the robot will be, it looks as if it's come back to the initial position, but not really. I'll explain why. Because the circle, right, I'm stopping the robot after it does one full circumference. You know, if I know the radius of the circle, I know the circumference, right? And so I'm checking to see whether it has completed a circumference. That's approximate. There's no way I can get it exact. Do you agree? In the real world, nothing is exact, 100% accuracy. So, it looks like that because, you know, I'm checking it so frequently that basically if it misses, it's missing by only a little bit. So, if you want to recreate the Gazebo scene as it was before, you can go up here and say reset world. See, it moved. Did you see it moving? It moved a little bit. So that's a good way to put back the Gazebo scene the way it was before. Okay, now I'm going to run it. I'm running it here, but you should look there. And I started it. It takes like a second or two to run. You can read. So by the way, you know what velocity is? Go and check the velocity and omega, divide one by the other and calculate the radius. You should get 2 meters. And look at it. Each of these squares is 1 meter. So 1 meter, 1 meter, 1 meter, 1 meter, right? So there's the 2 meters this way, 2 meters this way. And now it's coming back to the origin and it should stop. Now this is what you should see. Once you download the program, fix the IP address and run it, it should run. So, I asked you to plot. Here is the plot. How am I plotting it? I am recording its position. So the points along its path, right? The position can't be continuous. In any digital computer, you can't do continuous, right? Only the real world is continuous. On a digital computer, you can't do continuous. So I'm getting the samples of the points and plotting it. How am I getting those samples? So there is something known as wheel odometry. The rotation of the wheels, right, is being monitored. And on that basis, I'm figuring out where the vehicle is. We will see that later this week. So based on that, I'm plotting the circle. Maybe this line is a little bit too thick. But that can be changed in MATLAB. And you see a full circle, right? It started at 0, 0, right? 0, 0 is here. Can you see that actually it did not complete a full circle? See, it's missing a small piece. That's the real world. The real world will always be imperfect. But that's okay. If you don't park in your garage the exact same place as yesterday, you're not going to die. It's a good thing, right? We don't want that to happen. So precision is not important in the real world. In some, like surgery, it might be important, right? But even there, you can't have 100%. If two different surgeons did the same surgery, then they would do it slightly differently, and everything is fine. So tomorrow, this is what I'm going to do. I'm going to walk you through this code because your first exercise is going to be based on it. Now, typically robot programs are eternal. They run forever. Most of the time, the mission is such that it runs forever. For instance, let me give you an example. Suppose I have a sentry robot that is patrolling the perimeter of a house all night, right? Why would it ever stop? So long as it has battery power, it should go on and on and on, right? And what would you do in the morning if you don't need that? You would go and turn off the switch. So, if the program reflects that, the eternal nature of a robot task, then you will not get stoppage. The reason, see, the MATLAB is exited cleanly. I don't know whether I showed you that, but let me show it to you again. Oh yeah, so see here, the MATLAB has finished. If I make it to do something forever, then you will not get control back in the workspace, right? That's okay. How will you stop the MATLAB program because you're hungry and you want to go and eat? Control C. You kill the program with the Control C. Is that okay? So nothing to worry about. This program, I said, go exactly one circumference and stop. So it's a clean exit. Most programs will run forever because not because you want to run it forever. Most robot tasks, if you're driving a self-driving car, right? You're going on and on and on and on until you shut off the engine. So it's running for in an eternal loop. So tomorrow I'll explain the pieces of this for you. I've organized it, nicely with comments so that you understand precisely what each statement is doing. Then it'll be easy for you to work on your assessment exercise. In the beginning, as always, there is setup. You see, all of this is setup. Initialize RAWs, clean up the MATLAB environment, get the publishers and subscription. Remember I said publishers and subscribers? So that's where you get them all ready. So you'll find that if you think in those terms, in a modular fashion, code is not difficult to write. You have to think in a modular fashion. And I've structured the code accordingly. There's a lot of housekeeping you do in the beginning. And then the actual loop starts. Loop is where the fun is, right? All of this is set up, but the loop starts here. Okay, so I will see you tomorrow. So what is your task for tomorrow? You're going to make this program run and come back to the smile tomorrow. You can try all kinds of fun things. While it's running in a circle, drag a barrel and put it in front. See what happens. You're not going to crash anything, it's a simulator. You can't do that with a real car, right? So play around with it, see what happens. The important thing, it's a circle. Oh, I forgot to emphasize this. Let me tell you this here. Right here, see? Velocity v is 0.4. W, or omega, is 0.2. 0.4 by 0.2 is 2 meters. So it's a 2 meter circle. You may have noticed that in gazebo, the floor tiles.